Okay, third scenario is that there's no real roots to the auxiliary equation. So when you put it into your calculator, you'll get two complex roots. They will form a complex conjugate pair. So P plus or minus QI. Because we've got two distinct roots, you can consider this general solution. So we've got two distinct complex roots. So we can, this is similar to our first scenario. So we've got y equals a constant times e to the root times x plus d e to the root, other root times x. So same form. So we're going to consider this. I'm going to take this into an example. You can just prove this straight algebraically, but it's quite nice to see it with numbers in. And then in a minute, I'm going to give you a slightly different general form to use. So if you're copying this down, you might want to just leave a little gap here in your notes. So we're going to look at solving. d2y dx squared minus 6y dx plus 34y is equal to 0. So the first thing to do is consider the auxiliary equation, which I'm now getting bored of writing. And that is m squared minus 6m plus 34 equals 0. Pop that into your calculator and you get m is equal to 3 plus or minus 5i. So we've got this general form which isn't incorrect, but we're just going to rearrange it into something a little bit more usable. So we've got c e to the 3 plus 5i x plus d e to the 3 minus 5i x, and then I can pull e to the 3x out of both of these. So I have e to the 3x. Remember, when you multiply, you add your powers. So that's going to give me c e to the 5ix plus d e to the minus 5ix. And then this is a complex number, and so we can rewrite this with cos and sine. So e to the 3x, so it's in the form r e to the I theta, essentially. So this gives you c lots of cos 5x plus I sine 5x plus d cos of minus 5x plus I sine of minus 5x. I'm quite sure how many brackets I need now. I think it's 3 on the end of that. I can now rewrite this just pulling out these negatives like we've done quite a bit before. So cos minus 5x equals cos 5x, and sine of minus 5x equals minus sine of 5x. So it'll all factorise in a different way. Trying not to smudge my work. I probably will, having said that. So cos of minus 5x is cos of 5x. Sine of minus 5x is minus sine of 5x. Like so. And so I now have got e to the 3x lots of c plus d cos 5x and then I've got c minus d times I. So ci minus di sine 5x. And you can do this with any one where there are no real roots, so discriminant is less than 0. So that takes us to there. And then if we replace c plus d with a, and c minus d with b, sorry, I lots of c minus d with b, we end up here. So that this form, A, could A and B? B could certainly be a complex number because you're multiplying here by I, so you're not necessarily going to get real numbers coming up for A and B. So just something to think about there. The other thing, I'll show you some graphs of this, is that this is an oscillating function, and so when cos is at 0, sine is at 1 or minus 1, and when sine is at 0, cos is at 1 or minus 1. And it's actually used to model simple harmonic motion. So we will go on to model simple harmonic motion using second derivatives, but it's just quite a nice way of seeing where this work on sort of complex numbers that you've been doing is actually quite applicable to things in real life. But when we get to the simple harmonic motion, remind me and I'll show you some graphs of this as well. So just going back to that original thing, so this is the general solution, but it can be written as and this is the one we use, so it can be written as so y equals e to the px. So that's equivalent to me here having this e to the 3x. So that's the real part of my imaginary root. And then it's a cos qx plus b sine qx to there. Sorry, I didn't mean to go to it. I was thinking about something else momentarily. So that's that one there. I was just thinking I probably should just go to an example. I think I've got enough memory on my phone. So that's a general form to use when there's no real roots. So it's a really quick example. I've sort of done one already really, but just to show you that they are actually quite quick and easy. Let's grab this. So I've got second derivative plus h lots of the first derivative plus 17y equals 0, and then you find your auxiliary equation. So it's m squared plus 8m plus 17 equals 0. Work that into a calculator, and m is equal to minus 4 plus or minus I. And so from there, y is equal to e to the minus 4x, lots of a, just coefficient of I goes in here, so a cos x plus b sine x to there.